Hi, welcome to the Olympiad geometry. Let's continue our study. Before we start, if you think this video is helpful, please click the like button, comment, share, and subscribe to the channel. So, I prepared for the topic of conjugate medium. But during the preparation, I find that I need to introduce several other topics in advance so we can learn or get better understanding of the conjugate medium. So let's do this first. I'll talk about the generalization of the angle bisector properties. That's for the first part, and the second part I'll talk about the harmonic bundles, and then I'll talk about the Mikol theorem. So for the harmonic bundle, and also the conjugate medium, they are usually to be considered as advanced topic in plane geometry, but I think it's very useful when we talk about the projection later on, and which is a very powerful tool to be used in the Olympiad geometry. So let's just get started for this angle bisector properties first. Here we already know the angle bisector property, so which is that if we have a triangle here, let's call it ABC, and we know that AD is the angle bisector of the angle BAC. So we know that BA to AC equals to BD to DC, right? That's the angle bisector property. And we want to generalize it, which means that D cannot, D can be any point on BC rather than just AD is the angle bisector of angle BAC, right? So let D be a point on BC in triangle ABC, then we have this. BD to CD equals to AB sine angle BAD to AC sine angle DAC, right? This is obvious because we can just do this. BD to CD equals to the area of triangle BAD to the area of triangle DAC, right? And it equals to half of what is the area of triangle BAD? That's BA times AD times sine angle BAD to half of DA times AC times sine angle DAC. So you can see that AD cancel, half cancels. So we have BA or AB times sine angle BAD to AC times sine angle DAC, right? Exactly the same. And the second theorem of the generalization of the angle bisector would be we find 2 points, D1, D2, are on the BC in triangle ABC. If angle BAD1 equals to angle D2AC, okay, so now we have a triangle ABC here, and we find D1, find D2, and we know that angle BAD1, right? So let me. Okay, this is better. Angle BAD1, this angle, right? Triangle ABC, D1, D2 are on the BC. So angle BAD1 equals to angle D2AC. D2AC equals to this one. Then we want to calculate, or we want to say that AB squared to AC squared equals to BD1 times BD2 to CD1 times CD2. Right, basically, we actually can split this one to 2. It's BD1 to CD1 times BD2 to CD2, right? So we can use this theorem, the theorem 1, twice, right? So for the D1, we know that BD1 to CD1 equals to AB times sine angle BA D1. 2 AC times sine angle D1 AC, right? And for BD2 to CD2, we still use the theorem 1. We have BD2 to CD2 equals to AB times sine angle BAD2, 2 AC times sine angle D2 AC, right? And now we multiply them together. BD1 divided by CD1 times BD2 divided by CD2 equals to AB squared to AC squared times sine angle BAD1 to sine angle D1 AC times sine angle BAD2 to sine angle D2 AC, right? Notice that angle BAD1 equals to angle D2 AC, right? Angle BAD1 equals to angle D2 AC. So these two cancels. And angle BAD2 equals to angle D1 AC. So these two cancels. Then we can prove that AB squared to AC squared equals to BD1 to CD1 times BD2 to CD2, right? This theorem is usually called Steiner's theorem, and we will see this later. Okay, for the theorem 3. Theorem 3 is saying that let DEF are points on BC, CA, AB respectively. Then we want to have this one, so let's just check it. So it's like we have a triangle first, and we have A, B, C here. D is point on BC, E is point on AC, F is point on AB. And we want to calculate for BD times EC times FA to DC times EA times FB, right? So basically this can be split into 3 factors, which is BD to DC times CE to EA times AF to FB, right? And we know that BD to DC it equals to AB, see BD to DC it equals to AB sine angle BAD to AC sine angle DAC, right? And CE to EA, CE to EA, it equals to BC sine angle CBE to AB sine angle EBA, right? And AF to FB, AF to FB equals to AC sine angle ACF to CB sine angle FCB, right? So AC cancels, AB cancels, BC cancels. So we got this one equals to this part. This part is exactly this part, right? Sine angle DAB, sine angle DAB, sine angle DAC, sine angle DAC, sine angle EBC, sine angle EBC, sine angle EBA, sine angle EBA, and FCA, FCA, FCB, FCB, right? And you may notice this is already very close to the proof of Siva's theorem, right? Okay, let's see the next one. Theorem 4. D1, D2 are 2 points on BC in triangle ABC. Then we say that D1B2, D1C, 2, D2B2, D2C equals to sine angle D1AB to sine angle D1AC to sine angle D2AB to sine angle D2AC. Okay, so basically we are saying we have D1, D2 on the edge BC, right? And we want to calculate for D1B to D1C to D2B to D2C, right? D1B to D1C, we already know it. It's AB sine angle BAC to BAD1, right? To AC sine angle D1AC. So to D2B to D2C, D2B to D2C, that is AB sine angle BAD2 to AC sine angle D2AC, right? So here we have AB to AC and we divided it by AB to AC, so they cancel each other, which means we only have this sine angle ratio left, right? So that's sine angle BAD1 to sine angle D1AC to sine angle BAD2 to sine angle D2AC, right? Which is here. I just prove it. Okay. For the theorem 5, 3 lines are concurrent on point P. Line L1 intersects the 3 lines on A, B, C. Line L2 intersects 3 lines on A prime, B prime, C prime. Then we have this ratio that AB to AC to A prime, B prime to A prime, C prime equals to PB to PC to PB prime to PC prime, right? So let's draw it here. Let's draw it here. We have point P here, and we have A, B, C, A prime, B prime, C prime, right? So we want to calculate for AB to AC to A prime, B prime to A prime, C prime equals to PB to PC to PB prime to PC prime, right? We want to calculate for this one. So let's just see. AB to AC, what is AB to AC? AB to AC equals to half of AB to AC, that's the area of triangle APB to the area of triangle ACP, right? APC, so which is half of AP times PB times sine angle APB to half of AP times PC times sine angle APC, right? And A prime B prime to A prime C prime would keep the similar equation, which is A prime P times PB prime times sine angle APB to half of A prime P times PC prime times sine angle APC. Notice that A prime PB equals to sine angle APB, right? So these two, use this one divided by this one. Then we know that sine angle APB to sine angle APC divided by sine angle APB to sine angle APC. These two cancels, right? And AP cancels here, A prime P cancels here, half cancels here. So we know this one directly, AB to AC to A prime B to A prime C prime directly equals to PB to PC to PB prime to PC prime. right? Okay, that's theorem 5. Let's talk about theorem 6. Theorem 6 is saying that 4 lines are concurrent on point P. Line L1 intersects the 4 lines on A1, A2, A3, A4. Line L2 intersects the 4 lines on B1, B2, B3, B4, right? So 1, 2, 3, 4. We have 4 lines are concurrent on point P. And we have here A1, A2, A3, A4, and here B1, B2, B3, B4, right? Now we want to calculate the ratio that A1, A3 to A1, A4. 2, A2, A3 to A2, A4. Right? We want to prove it equals to B1, B3 to B1, B4. 2, B2, B3 to B2, B4. Because this L1 and L2 are arbitrarily chosen, so we just need to prove that this ratio is only related to these angles, right? And then it's obviously true. So think about this. What is A1, A3 to A1, A4? That eventually, and we have this 2 ratio, right? And eventually have this one, A2, A3 to A2, A4. That's eventually becomes a sine angle of this one to sine angle of this one divided by sine angle of this one to sine angle of this one. Nothing else changed, right? So, which means you can actually use your own arbitrary ratio, which just keeps these to be the same order or same form, right? Which is like, I can write it arbitrarily A1, A3 to A2, let's say to A1, A2, for example, then to so A1, A3 to A1, A2, then A2, A3 to A2, A4, for example, right? It must equals to B1, B3 to B1, B2 to B2, B3 to B2, B4, right? It's always the same. They cancel each other. It's just the sine angle ratios. Okay. So these are the generalization of the angle bisector properties. Basically, it's telling you that when you have the point on the edge, like arbitrary point, not the point that as an angle bisector, you can still have this kind of ratio here. And the most critical part, I would say, is this one. Because of this problem condition, that you can cancel all those sine angles, right? And then you have this this size only expression here, and this would be the most critical one in this video. And I would encourage you to remember this one, because we will use it repeatedly in the future. Okay. That's for today's video. I hope you like this video. See you in the next one. Thank you.